All right, folks, it's Bass Action back in action here. On this page of notes, we're going to get into the heart of this chapter, and that is our discussion about logs and exponentials. The most foundational piece that I want you to understand about logs and exponentials to really wrap your head around is the fact that they are inverses of each other. Okay? Now, that simply means that they are opposite operations. Now, if they're opposite operations, that's really no different than when we talk about multiplication and division being opposite operations or addition and subtraction being opposite operations. So what I've given you here are two sample functions. Now, these are not actually opposites of each other, inverses of each other, as I'll discuss as I get a little bit down in the bottom, but they're just a sample logarithmic graph and a sample exponential graph. So if I look at my first one here, my logarithm graph, what I can see is that I have a vertical asymptote, and I can also see that my graph is restricted to one side of the asymptote or the other. When I think about the behavior of a logarithmic graph, it's going to rise very, very quickly along the vertical asymptote, and then it's going to actually start to flatten out. So we could answer our questions about this graph. We could identify its asymptote as x equals 0, and we could identify the domain starting at that vertical asymptote of 0, but not inclusive, and going all the way to positive infinity. And I can identify that the range is negative infinity to positive infinity. So although we can't see when it actually reaches this value of 5, it will eventually get to a value of 5. It's just going to take a very, very long time to get there. Now, when I look at my sample function that I have here for an exponential, what I'm going to notice is that instead of a vertical asymptote as I had for my logarithm, I'm going to have a horizontal asymptote for my exponentials. So instead of an x equals, I'll have a y equals. I can see that my domain is certainly going to cover the entire spectrum of my x values. So my domain would be negative infinity to positive infinity. But my range is restricted to one side of the horizontal asymptote or the other. So my range will start at 0, non-inclusive, and go to positive infinity. So whereas our logarithms would rise very quickly and then flatten out, our exponentials are going to behave in an opposite way. They're going to start out very flat and then rise quickly. So what I want you to notice specifically about our logarithm is that our logarithms, since they have a restricted domain, that means we're going to have some rules we're going to need to follow. Our logarithms cannot be evaluated when they're either 0 or negative. So this actually combines together the ideas that we've been using with our fractions and our even roots. It actually puts it all together into one problem. Now, down here at the bottom, we're going to look at a couple special logs. We have a common logarithm, and our common logarithm has a base of 10. Okay? A common logarithm could be written, when we write our logarithm, as a log base 10. The base of the logarithm will be a small subscript, and then we would say of x. And more simply, the way you'll see this most often is just log of x. So because it's common, it's our most common one, we don't write the base, it's implied. So what I want you to notice is that this log x here, if we look at this log that I have up here, you'll notice that I didn't write the base. So the graph that I've provided for you up here is actually the graph of a common log. So log base 10 of x. We also have the idea of a natural log, and the natural log requires us to understand something else first, and it requires us to understand the number e. Okay, so we've got this number e here. Now e is really just an irrational number. It's not a variable. It's an irrational number that's really not much different for us than pi. Okay, its number is different, but its behavior is very similar to pi. So we actually have this formula to help us understand what E is. And we could go into a greater depth of this and how this formula comes to be. But what we ultimately are going to understand is that E is approximately 2.71828, so on and so forth. If you type it into your calculator, you'll get many more digits of it. But the idea is this, that as n, oops, forgot to switch back to my pen there, as the value of n approaches infinity, okay, so as our n value gets larger and larger and larger, so what we're looking at is this. So as this value right here gets very, very big, and up here, same number, as that gets very, very big, this entire expression is going to get closer and closer to 2.71828. So you could certainly try that out if you wanted. You could just start writing down some numbers. Pick a value for n, see what you get. Pick a bigger value for n, see what you get. Pick a bigger value for n, see what you get. And what you'll find is you're going to get closer and closer to that value. Now, the reason the natural logarithm is important to us is because, or the number e is important to us, is because a natural logarithm has a base of e. So we could write it as log base e of x, but more often, and when you look at your calculator, what you'll see is ln for our natural log x. So this is going to be the more common notation that you're going to see. So as we work through this chapter, we're going to move back and forth between these various notations of these two, and we're going to start to evaluate our logarithms even more.